Hi everybody, my name is Dylan Gaines and I'm from Michigan Technological University. Today I'll be presenting our paper, Methods for Evaluating Human Depth Perception in a Large Screen Immersive Display. So just a little bit of background. Distance perception has been studied extensively both in head-mounted displays and in the real world. Typically, these studies find that people accurately judge distances in the real world, but in head-mounted displays they tend to underestimate those distances a little bit. Now, there's a lot of different ways that we can measure these distance judgments, and these different methods can produce different results. However, the most common way to measure distance judgments is known as direct blind walking. In direct blind walking, the participant views the target either in the real world or it's displayed in their head-mounted display. Once they've viewed it for a little bit, the screen gets blanked or they close their eyes, and then they walk forward to where they think the target is. So it's kind of like when you walk into your bedroom in the middle of the night, and you just kind of have an idea of where your bed and everything is, and you don't run into anything. So that's kind of the concept that we're dealing with direct blind walking. However, with a large screen, direct blind walking doesn't really work, and that's because we can display the target in the screen, but the participant can't walk to that target because the screen's not going to move with them like a head-mounted display would. And so the motivation for our study here is that it's really important to measure distance judgments in a variety of ways because, as we've said, they can produce different results. So some of the current workarounds for large screens are verbal reports and triangulated walking. And with verbal reports, the experimenters display the target on the screen and just ask the participants how far away they think it is. With triangulated walking, the participants view the target and then they turn to the side and walk to the side, and then they turn back and point where they think the target is. And you can kind of triangulate the location of the target by intersecting the line that they were initially viewing the target along with the line that they're pointing at. However, we wanted to examine distance judgments in a large screen using the most common response measure in head-mounted displays and the real world. That's where it comes in handy that our screen is on wheels. So this allows us to move the screen to perform direct blind walking. Now this does change a few things. First off, it adds a waiting period between when the screen gets blanked and when the participant can start walking while we move the screen out of the way. It also adds a small gap at the bottom of the screen between the screen and the floor so that the screen doesn't drag on the floor when we're moving it. So just a broad overview of our study here. We used our mobile large screen display and we wanted to compare blind direct walking to triangulated pointing. And we did this using a between subjects design. So for direct blind walking, there have been several studies throughout the years that have performed visually directed actions to estimate distance perception. The most common of these are direct blind walking, and blind throwing has been used occasionally as well. Now, the 2013 survey paper on distance perception by Renner said that the walking estimates were quite good up to 25 meters, stating that they had no systematic errors, and that it showed the typical underestimation that we've seen in virtual environments. However, this paper also stated that the blind walking method was not suitable for large screens, which in most circumstances would be true, but in our case where we can move the screen, we wanted to challenge that assumption. With triangulated pointing, Klein et al. Compared triangulated walking, as they called it, to timed imagined walking and verbal reports. Verbal reports we've discussed already, but timed imagined walking is another method of doing distance judgments. In timed imagined walking, participants typically use a stopwatch, and they stop it when they imagine that they've walked to the target. And then the experimenters can get the distance from that using their average walking speed and the time that they imagined. In this paper, Klein et al. Compared these three response measures in the real world, in a cave environment, and in their display wall. Now, there was a general trend of underestimation of about 70% of the actual distance, and they had similar results across all conditions except the triangulated walking condition in the cave and display wall environments. We can see this in the graph here on the right. The horizontal axis represents the target distance, while the vertical axis represents the indicated distance. The solid black lines represent the perfect distance judgments, and the majority of conditions, as we can see here, hold steady at about 70% of this distance, while the triangulated condition in the bottom portion of the graph does not. Now, our study was the first of our knowledge to explore direct blind walking with a large screen display, and we wanted to compare this with other methods to improve our understanding of human perception. As we saw before, we had our direct blind walking condition where we have the participant looking at the target in the screen. And then we would move the screen out of the way and allow the participant to walk to where they think the target is. In the blind triangulated pointing condition, they would walk to the side of the screen. And since we didn't have to move the screen, we inserted an artificial delay of about 8 seconds to match the average delay in the other condition. From there, they would turn and point to where they think the target is, and we would be able to intersect those lines to determine where they thought the target was. Now, for our procedure, first off, we practiced blind walking with participants. So we walked them around the hallways with a blindfold on, just so they could get used to it and be more comfortable with it. Then, once we were in the room, for each trial, they would view the screen. Since our screen was not capable of stereoscopic display, we had the participants wear an eye patch so that their natural depth perception wasn't telling them that the target was at the depth of the screen. So they would monoscopically view the screen, get a good mental image of where the target was, and then they would put on their blindfold and we would blank the screen. Then we would move the screen to the side and let them walk to where they thought the target was. We used a Vicon tracking system to track markers on the hat that they were wearing so that we would know the exact distance that they walked each time. As I mentioned before, we had a between-subject design between direct blind walking and triangulated pointing, and we had 12 participants in each condition. So the first set of participants would do direct walking, and then the second set would do triangulated pointing. After that trial, they would then return to the starting point to view the next target and repeat. We varied our distance between 2 and 5 meters and found that there was no significant difference between the two response measures. We have a graph here showing our results for each condition, with the error bars showing one standard deviation. We can see that they were both fairly similar and close to the actual distance. The direct blind walking condition had an average of 89.4% of the target distance, while the triangulated pointing condition had an average of 108.5% of the actual distance. As we mentioned before, we were the first study to perform direct blind walking with a large screen, so we don't have any results to compare there, but we did find that our triangulated pointing results were quite different than those reported by Klein, since they reported underestimation of about 70% and less of the target distance, and we actually found slight overestimation. However, we did find high variability in our triangulated pointing results. Something that may have factored into that was the asymmetry of errors. What I mean by that is if someone pointed 5 degrees to the left of the target, the intersection point would be closer to the target than if they pointed 5 degrees to the right of the target. We actually had a few participants that pointed so far to the right that it did not intersect with the initial viewing line, so we had to drop those participants since we were unable to use their data. Though we didn't find a significant difference, we only had 12 participants in each condition, 10 in the triangulated condition after we dropped those 2 for analysis. And so we conjecture that using more participants may have shown a significant difference with the results we were seeing, but we didn't have a large enough sample size to make that conclusion. This all wraps into why using multiple response measures is a good idea, because of the trade-offs of variability and accuracy between the conditions. And it also is a slightly different task than with head-mounted displays in the real world, because of the delay, while the screen is moved out of the way. In conclusion, we did not find a significant difference between the conditions, but there was a higher standard deviation in the triangulated pointing condition. As for future work, we would love to be able to perform this study with stereoscopic viewing, which our screen was not capable of, as well as removing the screen bezels and the gap between the screen and the floor. Additionally, we would like to reproduce this study in the real world with the same delay between viewing and indicating. It would be interesting to see if any of these factors have an effect on the result. Thank you everyone for watching. We'll be happy to answer any questions during the Q&A session or in the conference Discord server. Thanks.